Hi, I am Midhu Michael, Assistant Professor, Department of Mathematics and Statistics, MES College, Marampally.
I am dealing with the topic applications of number theory. Before considering the applications, let's consider a puzzle. The puzzle says that there are certain things whose number is unknown. When this number is divided by 3, the remainder is 2. When divided by 5, the remainder is 3. And when divided by 7, the remainder is 2. What will be the number of things? How to solve these type of questions? Before consider the solution of this puzzle, we should have some previous knowledge. So we have some definitions. First one is, if A and B are integers, M is a positive integer, then A is congruent to B mod M means M divides A minus B. Or in other words, A minus B is a multiple of M. We use the notation for this. A is congruent to B mod M. That is, A can be written as B plus Km, where K is an integer. That is, B is actually the remainder obtained when M divides A. The other definition is inverse of A modulo M. If A and M are relatively prime, that is GCD of A comma M equal to 1, then the inverse of A modulo M exists, and this inverse is denoted by A bar such that A bar congruent to 1 mod M. So let's consider some problems. First one, find an inverse of 3 modulo 7. In modulo 7, we have only the numbers 0, 1, 2, 3, etc. 6. So the inverse of 3 modulo 7 is the number A bar such that 3A bar congruent to 1 mod 7. We have 3 into 5 minus 1 is equal to 15 minus 1, which is equal to 14, is divisible by 7. Therefore, 5 is the inverse of 3 modulo 7. But every integer congruent to 5 modulo 7 is also an inverse of 3 modulo 7. That is, the numbers minus 9, 12 are the numbers which is congruent to 5 modulo 7. So these are also the inverse of 3 modulo 7. Next, consider another example. Find an inverse of 4 modulo 9. In modulo 9, we have only the numbers 0, 1, 2, 3, etc. 8. So the inverse of 4 modulo 9 is the number A bar such that 4A bar congruent to 1 mod 9. So we have 4 into 7 minus 1 equal to 28 minus 1, that is equal to 27, is divisible by 9. Therefore, the 7 is the inverse of 4 modulo 9. And also, every integer congruent to 7 modulo 9 is also an inverse of 4. That is, the numbers 16 minus 2, etc. are also the inverse of 7 modulo 9. Then, next consider the puzzle again. The puzzle says that certain things whose number is unknown. When divided by 3, the remainder is 2. When divided by 5, the remainder is 3. When divided by 7, the remainder is 2. What will be the number of things? This puzzle can be translated into the system of linear congruences. X congruent to 2 mod 3, X congruent to 3 mod 5, and X congruent to 2 mod 7. Let M equal to 3 into 5 into 7. The product is 105. Then we let capital M1 equal to M divided by 3, that is 105 divided by 3 equal to 35. M2 equal to M by 5 equal to 105 divided by 5 equal to 21. And M3 equal to M by 7, which is equal to 105 divided by 7 equal to 50. Then Y1 be the inverse of capital M1 modulo 3. It exists because this M1 and 3 are relatively prime. M1 is 35 and 3 are relatively prime. And the inverse Y1 is equal to 2 because 35 into 2 minus 1 is equal to 70 minus 1 equal to 69 is divisible by 3. Second, Y2 be the inverse of capital M2 modulo 5. Then Y2 equal to 1 because 21 into 1 minus 1 equal to 20, that is divisible by 5. Next, Y3 be the inverse of capital M3 modulo 7. This is also exists because M3 is 15 and 15 and 7 are relatively prime. Therefore, Y3 equal to 1 is the inverse of M3 modulo 7. Because 15 into 1 minus 1 equal to 14 is divisible by 7. Then the solution X is equal to 2 into 35 into 2 plus 3 into 21 into 1, the inverse 1, plus 2 into 15 into and its inverse 1. The answer is 233, but converted into mod 105, the number is 23. Then let's check the answer. The x equal to 23, then 23 congruent to 2 mod 7. Yes, it is true because 23 minus 2 is 21 is a multiple of 7. Similarly, 23 is congruent to 3 mod 5 because 23 minus 3 is 20 is divisible by 5. Similarly, 23 is congruent to 2 mod 7 because 23 minus 2 is 21 is divisible by 7. Here it is 3. So it is divisible by 3. Okay. Then in general, it is proved by a theorem, Chinese remainder theorem. The statement of the theorem, let M1, M2, etc. Mn be relatively pairwise relatively prime positive integers and A1, A2, A3 are arbitrary integers, then the system of linear congruences the system of linear congruences x congruent to A1 mod M1, x congruent to A2 mod M2, etc. x congruent to AN mod Mn has a unique solution modulo M equal to M1 into M2 into etc. into Mn. And this solution is unique are congruent to modulo M to this solution. And the solution is x equal to A1 M1 Y1 plus A2 capital M2 Y2 plus etc. AN capital Mn Yn, where Mi equal to M divided by small mi and Yi are the inverse of capital Mi modulo small letter mi. And this is exists for I equal to 1, 2, etc. n. So this is the solution of the system of linear congruences. Thank you.